How's it going?
Actually, I'm having some issues with problem 5.
The bowling ball problem.
Yeah.
So where did you get stuck on that?
Actually, the very beginning. I've never actually bowled before.
Oh, okay. So I have a little demonstration to show what that looks like. So this is our bowling ball.
Okay.
So I'm going to slide this along, and you tell me what you see.
Okay.
Thank you.
Can you do one more time?
Sure.
So when you first pushed it, the bowl just slid along the table, and then at some point it stops sliding and starts rolling.
Mm-hmm.
So that's what bowling balls do?
Yep. So what do you think is involved in the transition between that initial sliding state and the rolling state?
Well, it's sort of sticking to the table, so maybe friction?
Okay. So if we've got an extended object that's rotating and we've got some forces involved, it might help to draw a torque diagram and see what we can get from that.
Okay. It's just gravity and friction, right?
Mm-hmm. So let's look at each of those individually. How much torque is gravity going to be putting on the ball?
I don't know.
Okay. Let's look at our ball. So if I set this up, how much torque is gravity going to be putting on the ball?
Oh, none, because it's going through the center. Right, okay, so all the torque is from friction, but that means that angular momentum isn't conserved. So how do I balance the torque?
What are you using for your reference point here?
The center.
Okay. Why?
Because that's where the ball is rolling around.
Okay. If you had to choose another point, which one would you choose?
Probably the point where the bowl touches the table, right here.
Okay, why is that?
Because gravity points through that point, and then so does friction.
Okay, so what does that mean?
So if we pick that point, there's no torque.
Are you sure?
Yes? Yes, I'm sure.
So this is actually one of the more difficult things in this problem, is choosing where to put that reference point.
Okay.
So now we've got a situation where there's no torque. That means angular momentum is conserved. So that usually means that we're dealing with an initial case and a final case. So what are our initial and final states for this?
Well, I guess it makes sense to consider these two different types of motion. So the initial state would be when it's sliding but not rolling. But if it's not rolling, how does it have any angular momentum at all?
This is actually one of the things that bothered me when I was learning about this. So let's look at the center of mass for the ball. Right? What's happening when the ball's sliding?
It's moving.
Okay, can you draw that on the diagram for me?
Yeah, so it's just going... Okay, so I guess now I have to include the sliding part and the rolling part, which includes all the moment of inertia stuff.
Yep.
And I can't assume that v is still the same, right?
So what if the velocity was the same before and after? What would that change?
Well, it would mean that it couldn't be rolling because it has to slow down before it starts rolling. I guess that makes sense.
Okay. What if we did this on like a concrete floor or on ice, or how would the surface change things?
Well, if we were on concrete, it would basically just roll immediately. And if we were on ice, it would slide for a long time before it started rolling.
That sounds about right.
Okay, so I think I actually kind of get this. So I'll need to use the I for the rotation of a sphere about the center.
Does your answer make sense?
I think so.
Okay. Show me.
Okay, so before, the ball is just moving down the lane with linear velocity v1.
Okay.
And then after, it is also moving down the lane, this time with linear velocity v2, but it also has angular velocity omega 2. And because both sides of the equation are equal, v2 has to be smaller than v1. So yeah, it does make sense.
Sounds good to me. Nice work.
Thanks.
Pause the video here. Finish up your notes on what the TA did or didn't do to make sure the student was following and understanding. In the next section, we'll show you what we noticed. Instead of diving right into the problem, the TA starts by asking the student where he got stuck. Diagnosing the student's problem allows the TA to know what to focus on. By approaching the problem this way, the TA is modeling how experts approach and solve problems, and is providing the student with a model for problem solving in future. Also, when the student says he's never been bowling before, the TA uses a demo to help the student understand the problem conceptually before diving into the math. Here, notice how the TA asks lots of questions to help the student along. He's not doing the problem for the student, he's helping the student do the problem for himself, and only helping where it's really necessary. Also, asking questions gives the TA a sense of where the student got really stuck. By the way, the TA does this throughout the entire video, we just picked this section as one example. Here, the TA asks a leading question. Are you sure? Even though he knows the student is right. This forces the student to stop and think about their answer and build enough confidence to say, yes, I'm sure. The TA takes a short break in the rhythm of problem solving to point out that they've figured out the trick of the problem. This builds confidence in the student and also allows for a bit of a mental break before finishing up. Here, the TA empathizes with the student, saying, oh, this bothered me when I was learning about it. So the student hopefully realizes that the TA is human too, and wasn't magically born with the knowledge of how to solve bowling ball problem number 5. So here the TA takes the problem to its logical limits, if friction was very low, as it would be on ice, or very high, as it would be on concrete, and asks the student to explain how that would change their answer. The TA is making sure that the student understands the problem conceptually and isn't just plugging and chugging. Experts often consider limiting cases to get a sense for the bounds of their solutions, while novices rarely do. Here, the TA is helping the student move along the continuum of novice to expert problem solver. After the student solves the problem, the TA makes him justify his answer, as a final check that the student has fully understood everything. This also builds confidence in the student. Now, he might even be able to explain the problem to his friends who missed office hours.